now we're going to move on to our second speaker of the day, Mahima Mary Mathews. Mahima is a PhD scholar in cryptography and quantum technologies at the Indian Institute of Information Technology in Kottayam. She did her MT Tech with specialization in data security from CUSAT University with a university first rank. She developed a novel scheme for secure communication, achieving authentication and integrity for resource-constrained delay-tolerant networks during her master's period. She's also a core and application programmer with industry experience at Accenture Services. Her research focuses on post-quantum cryptography, quantum programming, quantum cryptanalysis, and quantum communication protocols. She is a research coordinator and consultant at Cyber Labs at her university right now at IIT Kottayam, and is part of multiple industry-funded projects. She actually received a research support from IonQ, a quantum computing company that provided access time to the IonQ trapped ion quantum computer, which is worth $10,000 for her proposal in post-quantum public key infrastructure as part of the IonQ Research Credits Program. And finally, she's programmed on quantum computers from IBM, IonQ, and Xanadu Quantum. Mahima, you're just incredible. She'll be presenting on the impacts, challenges, and promises of quantum technologies and cybersecurity. So let's please give it up with a virtual applause for Mahima. I will stop sharing.
I am audible.
We can hear you.
Okay, good. I think there is a delay. Yeah, but it's fine. So thank you for inviting me to this session and being with you all. It's such a great experience to be with such a group. So yeah, without wasting time, I think we can go to the session, right? So I have got an extra 4 minutes. Okay. Okay. So today, technology that we're considering and discussing today is basically quantum technologies and introduction to it. And from the organizers, I came to know that like you people are very new, and there could be people like who have some knowledge in it. So considering all this, I have like tried to make it very simple, as well as like make you understand what is really important to know in this area. So that's what we'll try to cover. Whenever you have a doubt, please, is it possible for everyone to type in the chat window? Or how can they like let me know?
Yes, it's possible for everyone to talk in the
chat.
To write a message in the chat.
Okay, good. So then whenever you have a doubt, please type it in the chat window then and there, so that I'll take regular breaks in between to look into it. Okay.
Awesome.
So with that, we'll start. So now, like I would like to start with an introduction to quantum computing, basically. So you all are familiar with quantum mechanics, quantum like technologies, at least the terms, right? So what is quantum mechanics is basically like what is different from the classical mechanics is basically that in classical mechanics, you were dealing with objects that you could see or touch or something like that, right? Whereas in quantum mechanics, you start dealing with objects, which is like beyond our like imagination, like which we cannot see directly, which comes to like molecules, atoms, and electrons. So definitely, I'm not getting into theory basically, but so definitely whatever definitions are there in the classical mechanics, they are not applicable or available in quantum mechanics. So definitely there is a theory of or a set of like classical quantum mechanics basics, which is dependent on like or describing effects like superposition, entanglement, interference. So here you can see a small animation of like the showing a cat where it is in both states of like alive and dead, like until the time we open the box, right? So this is very familiar, but I thought of recapping it with very good animations. So then other important concept that you have heard is like superposition, where until the time you observe, you will have states in both zeros and ones. Then another important concept that we have is entanglement, right? So these sort of phenomenons or quantum effects are not available in classical mechanics. So that's what makes it different from classical mechanics, right? So now what is quantum computing? So basically, quantum computing is actually a type of computation where you deal with operations that harness these phenomena. Okay. Now, any computers that is able to compute at using making use of these effects is called as quantum computers. So basically, what we're trying to do is in classical computation, what we were doing is we were encoding information which is in the form of ones and zeros. Classical phenomenon of like voltage high and low and such cases. But now what we're trying to do in quantum computing is basically what we're trying to do is we are encoding information and we're trying to make use of that encoding information into some phenomena or like these matters that we talked about in the quantum mechanics. And then we are trying to harness, make use of these quantum effects to do computation. So by this, you should be clear, like what is the computing, how it is different from classical computing. Now, that's about these computing. Now, why people are telling that it is going to destroy our classical security. So to understand that, we'll have to start with how the current classical security looks like, right? So classical security, like there are a lot of approaches. Fundamental approaches that we have is symmetric encryption and asymmetric encryption. So just understand that in symmetric encryption, we will have a message and Alice and Bob, they will share the same key. Okay. So what Alice will do is Alice will take the message, encrypt it using the key that Bob already knows. Okay. And using this key, the encrypted message is generated. Now, Bob, since he knows this key, he can decrypt it. So if you are not even familiar with what is Alice and Bob, it's actually the communicators and common analogy used in cryptography. Like the people who are trying to communicate is called Alice and Bob. Okay, they are the good people, sort of like they are trying to communicate. And Eve is the attacker. Okay, so if you are very new to cryptography and security concept, just understand like anybody who is referring to Alice and Bob, this simply mean the sender and the receiver. Okay. So the sender is usually referred to as Alice and the receiver is Bob and the attacker is Eve. Okay. So what I'm trying to tell here is in symmetric encryption, Alice and Bob will have some key which is shared between them. Okay. And using this key, which is shared, since it is shared between them, only they can read the information, right? So it's important that this key has to be distributed securely also, right? So if we have a like box in which the message is like kept secret and the key that we use to open that box, that key is very important, right? So it has to be securely transmitted as well. So that's the concept of symmetric encryption. In asymmetric encryption, the difference is that it is sort of like mathematically derived pairs of keys. So each person will have his own pairs. So Alice will have his her own public and private key pair, and Bob will have his own like public and private key pair. Now, what the concept is that if you are encrypting with a certain party's public key, then you have to decrypt it using the certain party's private key. Like it's like a pair. You open with, you close with one of the keys of one person, then you will have to get the pair to unlock it, right? So that's basically asymmetric encryption. The difference is that it is mathematically derived as compared to symmetric encryption. So it's basically like you have a computation where you have some x operated with y is equal to some z, then you and y will be kept secret, and only the person who knows the y value can be able to regenerate the c value. So something like that. So it's mathematically derived, and that's the beauty of it, right? Now, so to sum up, like classical cryptography is basically like on symmetric encryption, asymmetric encryption. Then we have also have hashing schemes and digital signature. Hashing schemes and digital signature is basically like hashing is used for ensuring the integrity of the message. Like integrity means like if Alice is sending a message to Bob, Bob has to check that the message is not modified. So how will she do that? So what, how will he do that is like when Alice is sending the message, along with the message, she will also send the hash value of the message. Okay. So when Bob receives the message, he will again construct the hash value at his end, and he will compare the hash value that was received and he generated. So if both are same, then it means that his received messages, right? So that's basically hashing. So now, like even though we have these two schemes, like we can say that the fundamental security infrastructure depends on the secrecy, right? So for secrecy, we have some sort of concept called keys, right? So in cryptography, the cryptographers believe that a system is should be considered secure even if everything else about the system is revealed, but key is kept secret. So what I meant is like, as per cryptographers, a system is expected to be secure even when everything about the system is revealed except the key. Okay, so that's the strength of the key. So now what like keys looks like in symmetric encryption is usually pseudo random number generator. So we generate a random sequence of ones and zeros. Okay, and in the common used encryption schemes are AES, triple DS, etc. And asymmetric encryption is dependent on unsolvability of mathematical problems. So, for example, the factorization problem. So, in factorization problem, the example is RSA 2040. So, what RSA 2048 means is that RSA or how RSA 2048 is secure is that for breaking RSA 2048, an attacker or the Eve should be able to capable enough to break a factorize a number of 2048 bits. So please imagine like a 2048 bits number. It's very huge, right? So in order to break RSA 2048, Eve should be capable enough to factorize a 2048 bit number. So it's very huge and it will take millions of years. So that's why we say that RSA 2048 and 4096 and all is secure, but as we come lower like 1024 or 512 and all is like not secure, because with current computations we can do that in like 1 year or something like that. So asymmetric encryptions are dependent on unsolvability of the mathematical problem. So as I told, like asymmetric encryptions are derived from mathematical security or mathematical combinations. So in order to break an asymmetric encryption, the attacker should be able to break that mathematical hardness. Whereas in symmetric encryption, they should be able to find what was the random number generated in the place of key, right? So now you have a context like asymmetric encryption commonly used examples RSA, ECC, etc., and SHA and DSA. So this is a good point to like summarize what we learned till now. So classical cryptography, we have like symmetric and asymmetric. And in order to break these systems, to break symmetric encryption, we had to predict these as the key input. And in order to break asymmetric encryption, we need to break the mathematical complexity on which their security is dependent on. So in a situation where we have somebody who can predict the random numbers that were used, or we break the unsolvable problem that they were using, these cryptographic schemes becomes unsecure, right? Now, what happened with quantum computers? So this classical cryptographic systems were perfect, right? So suddenly, why people are telling that they are not good? Why RSA is going to be broken? So what happened is in 1994, Shor proposed this algorithm called Shor's algorithm, which is capable of factorizing and 2048-bit number in polynomial time. So what is a polynomial time is that you can fix, like you can evaluate, like it does not, or if it is coming in a usable period of time of the data. So I'll explain what is usable period of time. So what happened is that, as I told earlier, with the classical computer, it was very difficult to factorize a very big number, right? So with Shor's algorithm, he reduced that complexity to a very small range. So when the place where it was taking millions of years, now it is predicted to take just 8 hours, 3 hours, like that. So like it's questionable, right? So classical cryptography started getting weakened because especially the asymmetric key encryption. Why? Because most of the asymmetric encryption schemes, asymmetric encryption classical schemes that we use today were dependent on mathematical complexity, and they were directly linked with factorization problem and discrete logarithm problem. Unfortunately, Shor's algorithm is an algorithm that can reduce their complexity, which means that it is an algorithm that can solve the mathematical problem that they were relying on. So what happened? Even though the advancements in quantum technologies were good, it had a negative impact on a different sector, right? So every coin has two sides. Similarly, one advancements in the other side produced an algorithm, but that algorithm impacted the classical cryptography, and now like it's sort of like the entire asymmetric crypto systems that we are relying on cannot be usable when we have a good powerful quantum computer in place. Yes, it will take some more years, but still it's time that we get ready. Now there is another important contributor, that is Grover's algorithm. As I told, if you remember, like symmetric algorithms are actually breakable when we are able to predict what key was used, right? So symmetric algorithms, it's sort of like searching the key from the entire set. So Grover's algorithm reduces the searching time, and it can be used in combination with other algorithms to even reduce the complexity of symmetric schemes. So this impacted, like, let's see how it impacted. So symmetric algorithms are like okay-ish, but asymmetric encryptions that we had is sort of broken. Now, how symmetric encryption can be made okay-ish is like we will use large keys, because as we know, Grover's algorithm did not, like it's still dependent on big of root n. So as we increase the range of the n, still the complexity is there. But asymmetric encryption, it's completely broken. We need to replace with quantum safe solutions. And again, for hashing and digital signatures, we basically need longer outputs. Okay. So at this point, I look into the chat. We have, if you have any questions. Not able to see the chat. Okay. So there are no questions, right? Is it clear till now?
I think that
Okay.
there's a question right there.
Okay. symmetric and asymmetric. I'll just go to that slide because it's very important to go ahead. I'll just try to give you a small brief again. So symmetric encryption, if you remember this slide, so if you remember this slide, symmetric encryption uses the same key. That's why it's called symmetric or single key concept. So it uses like, if you know, like if I and Sabina decides like, instead of A, I will replace with Z, okay? And instead of D, I will replace with E. So if I create an alphabet set, which is known to me and only Sabina, what I can do is, until the time we have that mapping, right? I can send these, if I need to send apple, I will substitute apple with that key. A key is, what is that? It is a paper which has the mapping, right? So that's actually sort of the symmetric key. Like you have a mapping from every alphabet to another alphabet. So that's a key which is common to both me and Sabina. Okay. So any person who has that key only can decrypt. So since we had secretly managed to create that key, only we both can decrypt that message, okay, or read that message. Whereas asymmetric encryptions is concept like, it's mathematical. So you have to understand, like, I'm not sure how bank lockers works in your place, but in India, I'll try to explain, like, you have a key which is like, which is with you, and there is another key which is with the manager. Okay, so it is like pairs. Okay, so only if the corresponding pair with the manager's key, both are used at the same time, it will be opened. It's not exactly the same, but it works in pairs. So if I have a key pair of public and private key, and I am encrypting with my private key, Sabina should use my public key to decrypt it. So it's like bit technical, but just understand that it is sort of mathematical and it works in pairs. And we have two keys at both the ends, and it's mathematical. That's the important thing we need today. Like it is dependent on the mathematical complexity, and that complexity is broken by quantum computers. That's the input that we need. Hope that is clear. Yes. Cho's algorithm makes use of quantum phenomena to reduce the, to factorize. It's actually directly discrete logarithm problem. We can extend it to factorization problem. Okay. So clear till here? All good? Thank you. So I think now we can go, like, who should worry? Like, okay, we told that Show's algorithm is there, Grover's algorithm is there, classical cryptography is there. It is going to be broken, but still we know that these quantum computers take some more time to be in existence, right? So should we actually worry? Like, who needs quantum safe solutions? That is a very important question. So you guys, like being in your exact like I'm not sure how it is called, like matriculation or like +2. Here it is called +2, like when you like pass in just before the undergraduation. So this age is like where you can drive yourself, right? And this like sort of solutions could be requiring much more dedication, and if you guys focus, it could be a very good area that you can get into. So try to understand this. So like, what is the problem with now is, like, we know that quantum computers will take some more time to come into existence. But there is a problem called lifetime of the data. For example, my health information or your health information. It is important throughout your life, right? Until our lifetime, it is very important. So if it was encrypted using an RSA algorithm, or the base behind the security for that data was RSA algorithm, RSA algorithm will get broken in maybe 10 years, but that data is still valid, right? So there is a problem of storage and attack. So now what attackers are doing now is, even though they don't have access to quantum computers right now, they can store these very important information. Like for example, defense information is like very critical for a country, right? So they can store like our defense highly confidential informations and all. It might be secured using these algorithms. They can store it. Let it take 5 or 10 years, okay, for the computers to come into existence. These data could be broken and visible to these attackers, right? So that's very important consideration. So if the lifetime of the data that we're dealing with is more than the expected time for the quantum computers to come into existence and break these algorithms, then you have to move immediately. Okay, so I hope that point is clear. So that's what exactly this Mosca's theorem says. Like if you need to keep the data alive and it is valid data even after the quantum computers come into existence, then you have a problem and you need an immediate shift. Okay, so now that alerted a lot of thoughts in cryptographers and security solution companies from all over the world started working in quantum resistant cryptography, and people started proposing a lot of solutions. And you have to understand that this is not new. Okay, people were working on quantum resistant cryptography like long back, but suddenly what happened is like the the growth in the quantum computing technology, especially because of measurement methods, and people started like IBM, D-Wave, they started scaling up the expected qubits, and the growth seems to be like very fast, so that the chances of quantum computers being powerful enough to break a practically used RSA is very near, that we need to think about quantum resistant solutions. Okay, so now what are the quantum resistant solutions we have? So the first approach quantum crypto systems is obviously quantum destroyed. Now quantum based phenomena are the solution. Okay, so first is quantum phenomenon based cryptographic system. So we make use of quantum phenomena like superposition, entanglement, or no cloning theorem, such phenomena to create crypto systems. Okay, so that is basically quantum phenomenon based crypto systems. So under that we have like quantum cryptography. Right now there is no superclass, subclass, proper categories. Yes, there is, but people like what should I say? Like when they refer to quantum cryptography, they could be referring to any of the cryptographic solutions that is dependent on quantum phenomena. It may not be like quantum networks and all. So, but it is evolving, and there could be proper classifications that we can see in the coming days. But all these, what I have listed here are some of the phenomena, the solutions that are dependent on quantum phenomena and is resistant to quantum attacks. So for example, QKD is an approach where we distribute keys. So if you remember symmetric keys, we had that same key, right? We had the paper that I had Sabina and Sabina set up, right? So that paper is actually very important, right? So that key that Sabina and I shares, it can be distributed using a QKD. Okay. Now we can use classical crypto systems for encryption still, but the key is very important. I can use quantum based solutions to distribute that key. So that is QKD. Then we have quantum random number generators. So those are like, as I told, pseudo random number generators are based on some phenomena which is deterministic, like it is capable enough to run on a classical computer. And you know, if you have learned the theory that anything that can be run on a classical computer is sort of deterministic, right? because it has states, and if you know the states, you can sort of reverse it. So it is deterministic. Whereas in quantum phenomenon, it's not, you can make it non-deterministic, right? So there are like beam splitter experiments. Yes, there are debates on like based on the conditions, it can be like not 50-50, and if the splitter is not good, that I'm not going into that. But in ideal case, you have a 50-50 probability, right? But again, there are, if you are from pure physics background, there is another debate that a pure randomness, you cannot even predict 50-50% possibility. So that's what quantum provides a promises. You can have true randomness. Okay, so that's what quantum random number generators promises. If you make use of quantum phenomenons, which are like truly random, you can produce random numbers which is not at all predictable. Okay, so that's there. Then quantum secure direct communication is there, and QSS. Now, if we cannot like wind up the session without discussing a little bit about one of the QKD protocols. So I would like to introduce one of the please remember, this is a QKD protocol. What is it? Quantum key distribution protocol, and it is BB84 protocol. And recently, BB84 protocol, the compilers of BB84 protocol, they won a lot of awards in the quantum information processing, if you have been following. So it's a very, very important protocol that showed the possibilities of quantum cryptography. Okay. And you can see it was developed in 1984, not very recently. So that's why I told it, these solutions were very long back. But now currently, because of the situations that the quantum technologies are advancing, we are sort of like looking into it more seriously. Okay. So how BB84 protocol works is, we'll have a classical authenticated channel and a quantum channel. Okay, as you can see, quantum channel is like one direction. Whereas in classical authenticated channel, I have drawn it like two directional. So only the sender is sending the photons to receiver. Okay, so this is a prepare and measure protocol. So sender prepares certain photons in certain polarizations and send it to receiver. And attackers can have access to both the channels. So this is the setup of BB84 protocol. So how it works is, we have 4 polarizations possible. So like for 0, there is like 2 polarizations, which is like with degree 0 and with degree 45. And for 1, we have for 90 and 135. So as you can see, these 2 are in rectilinear basis, and these 2 are in diagonal basis. So in order to measure it properly, I should use the matching filter. So this photon, if it is in this basis and I'm passing it through a rectilinear filter, I'll get the measurement correct. Okay, I'll read it as 0 itself. But if I am passing this one through a diagonal basis or diagonal filter, then I'll get random result. Okay, clear? So in BB84 protocol, the sender or the Alice, she has 2 ways to encode 0, and she has 2 ways to encode 1. Now, Bob, what he does is, he will try to predict, okay, Alice would have used this one. So he will like use rectilinear basis filter. Now, if he use correct matching filters, he will get the correct data. If not, he will get random output. So likewise, he will be generating the values. So to give you a good visualization, I will be using so this is actually a BB84 protocol demo sort of setup. So here you can see that this is the Alice source and this is Bob. So here Alice is going to encode it in X basis, and Bob is also going to measure in the same one. So if Alice will send one particle, so here you can see that Alice is sending 0. Bob is also getting it in 0. So suppose he does it in different one. What happens? See, their basis is non-zero. So like we can see that none of it is matching. So because Alice encoded in X basis, whereas in Bob is using Z basis, right? So this is like, I mean, this is a like very worst situation where everything goes wrong. So we can see that when Bob is randomly predicting it, so if it is like random orientations, we can see that there is like random 50-50 chances of, see here, there is 50-50 chances of Bob making the correct prediction. Clear? Any doubts there? Have any doubts? You can ask. Good. With this animation, it's very clear, right? Because you guys can, I'll just put this link also in the chat window. You guys can play around with it. So yeah, and also this particular website has a lot of simulations like this. Okay, if you're trying to, I think many of you guys will be familiar, but still I'm telling, if any of you doesn't know, this particular website has a lot of like simulations like this, which is related to quantum like theory. Okay, so I think BB84 protocol is clear. So there is like chances of Eve's interference. We are not getting into details of that, attacks and all, but how BB84 protocol works and how we make use of quantum phenomenon to securely transmit the keys. Now, after this, what happens is Bob announces. So we had a quantum channel here, right? We had a where is it? We had a classical channel and a quantum channel. So quantum channel is where these photons were transmitted. Now, what is the role of this authenticated channel is there is concept called sifting, where Bob announces his measurement basis. So only this basis is announced. Like he will say, I have used Z, Z, X, X, Z, X. So saying this, Alice will be able to predict which of the ones Bob has made correct. So Alice will tell, okay, you have made a mistake in the third prediction, just discard it. So what happens is when he discards this one, they both will end up with the same key. Okay. So that's the concept of sifting. Sifting, okay. So that's how BB84 protocol works. And this is one of the approaches where we make use of quantum phenomena. As I told, it is like one of the approaches. It is what we discussed is BB84 protocol. It is QKD protocol. We have QSTC, QSS, then secret passing, like multi-party sharing. Lot of approaches are there which you can dig deeper in. Okay. So now that is based on quantum effects. Now what else can we do? Is that the only solution? Because quantum based phenomena, as you have seen, you need photon sources, you need, or either you need fiber channels which is capable of doing these photon transmission. You need measurement devices. Lot of hardware upgradation is required for these networks to adapt these like crypto systems, right? So that's not very feasible, right? Because the infrastructure that we have today, the internet infrastructure that we have today, it was built with a lot of years of hard work. So, and it is like working sort of perfectly also in many of these scenarios. I'm not telling it's completely secure, but it's sort of okay with in many of the scenarios. So suddenly, if we ask to shift into something new, it's not very easy, right? So we also have alternate solutions, which is called post-quantum cryptography standards. So which is based on families of problems considered to be quantum safe. So that term is very important, considered to be quantum safe. Why? Because see, quantum computers was not a new ideology or a new concept, right? Even when RSA was out there and working perfectly, people knew that quantum computers are going to be a reality someday. Until Shor's algorithm was there in place, which showed how quantum computers can be used to break or solve a factorization problem. Nobody like understood the possibilities, like really to be true. Like that's where people started realizing the possibilities of it, and how it impacted the classical crypto systems is also one strike on the head for everybody, like to really take it serious also. So post-quantum cryptography, again, if we stress on, is a family of algorithms like factorization problem, which is not solvable even to a quantum computers. So quantum computers is not a universal problem solver. There are still problems which is difficult for a quantum computer. Now what we do is, we will take such mathematical problems which is difficult for a quantum computer, and we will build crypto systems on top of that. So the example is lattice based. Okay. So in lattices, there is a problem called shortest vector, which we'll see in the next slide. So that is still a difficult problem for quantum computers until another shore or somebody among you will develop an algorithm to solve it. Okay. So until we have an algorithm which can solve it in polynomial time, it is considered hard. Okay. So post-quantum cryptography is like similar to classical cryptography, but the difference is that they are based on mathematical problems, which are mostly geometrical. Okay, if you look at these problems, they are in geometrical problems that they have adopted. So these geometrical problems are actually hard for quantum computers. Okay, so under that, we have public key encryption, key encapsulation, and signature schemes. Now, what should we go for? Wherever possible, we should go for hybrid architectures, and immediate shift will be post-quantum cryptography. Okay. And today I would like to introduce lattices also to you, which is actually part of the post-quantum family. So what is lattices is, it is a set of points of n-dimensional spaces with a periodic structure. And as I told, there are basically three problems that we rely on, that is shortest vector problem, closest vector problem, shortest independent vector problem. And there is a concept for good base and bad base. So I'll introduce everything. So this is a lattice. So you have to understand that lattices, this what I have projected before you is a two-dimensional lattice. Okay. Lattices can be in n-dimensional way, and n can be infinity also. So you have to understand the geometrical complexity of lattices. Okay. So this what I have projected is a good basis. So imagine that you only have this vectors. Okay, you don't have these dots. So when you have this much information, this vector information, when it is this one, it is very easy to reconstruct the other vectors, other lattice points, right? Whereas if you have this one without the other dots, it's not very easy to reconstruct the entire lattice. So that concept is good base and bad base. So if you will be able to predict the structure of the lattices using that particular base, they are considered good bases. And if it is like not very easy, it is called bad bases. So now what is hardness is, so I'm talking about the nearest point hardness. Okay, so I have placed a purple point near to this. Okay, see on both this situation. So when I am using a good basis, I can easily reconstruct the entire lattice and say that this particular point is the nearest closest point. Whereas in this situation, since this particular base is a very difficult base, okay, to actually reconstruct, using which I can reconstruct their lattice. So to point out that this particular point is the closest point, lattice point to this particular purple vector, point in the space, this purple vector, then it is very difficult. So that's the hardness here. Now imagine this is actually a geometrical problem, and you will be looking at lattices of n dimension. So when you have a bad basis in your hand and you have a point somewhere in the space, and you are actually asked to predict what is the closest point to it, without a good base, it's not very easy to reconstruct it and predict the place. So that's the hardness we have. That is difficult even for a quantum computer till now, because we don't have a quantum algorithm that efficiently solves this problem. Okay, so that's what lattices relies on. And NIST is already like they have been looking into these post-quantum crypto solutions from 2017. They have released their initial set of candidates, which is possible to be like the standardization algorithms. And here you can see that crystals, dilithium, and falcon is based on, or first, all three are based on lattices. So that's why I thought it is very important to introduce lattices and its hardness to you today. So all the first three is based on lattices, and the first one, Kyber, is based on lattices along with learning with error concept, and this is based on shortest vector problem. And Sphinx is actually a hash-based signature scheme. Okay, so this the first one is all for public key encryption, and the last three are all signature schemes. Okay, just introducing all of them to you. So with that, I feel like you got a like glimpse of what quantum impact is on classical cryptography, what impact it has on classical cryptography, and why we need to be getting ready for this quantum era transition. And it's also considered to be the biggest security transition ever, because it also requires hardware upgradations to some extent if we are going for quantum based solution. So yeah, so there is a lot of things that we can do. There is a lot of requirements here. I hope you got an idea. So thank you all. And any other questions are like.
Thank you so much, Mahima. That was amazing. I know for me personally, as someone who's like really fascinated with everything cyber, this has been truly eye-opening. So for all of our attendees, please put as many questions as you want in the chat or in the Q&A box as well.
I wanted to also thank you, Mahima, for this great presentation. It was amazing, and I could learn a lot. Thank you.
Thank you.
I have a question, or
Yeah.
actually we have a question. What is the future of quantum computing?
Is it quantum computing or quantum cryptography?
Cryptography.
Okay, in this context, most probably QC should be that. Okay, one interesting thing for you guys to do, like, can you all simply search on Google and tell me what is a Q day? Q day. You guys will have heard, at least some of you, what is a Q day? Q day is something very important that every cryptographers and security field is like scared of, and you guys should know what a Q day is. So who will be the first person to put the answer in the chat window?
Has anyone researched yet?
You can search on Google, it's an open question.
Okay, someone put in the chat, Q-Day represents the day that quantum computers will reliably use the superpositioning power of multi-state qubits to break encryption algorithms.
Exactly. So they currently, whatever classical crypto systems were discussed about, Q-Day is, there is a company who has set up a like countdown on the Q-Day also. They have put it around 2014, April 14 or something like that. So yeah, that's a prediction from them. Like they're predicting that this quantum computers will be so powerful enough that everything practical that we have today will be broken. So to answer specifically the question, what is the future of quantum cryptography? It should exist actually. So right now we are having a lot of challenges, like for example, BB84 protocol, it requires single photon sources. So right now we have hardware challenges, like we can't have a proper photon sources which emits single photon at a time. So since BB84 protocol is relying on that single photon existence, there is practical implementational issues. That is what we are at right now. And there is fidelity issues, there is Cuba estimation issues, then we have environmental attenuation. Again, we have Eve's issues as well. So how to predict the presence of the Eve? These are where we are having issues. It's not that quantum cryptography don't have a future. There is, and right now everybody is trying to implement it. That's the stage we are. There is no going back now. From my analysis and my experience, we have taken a stage where now we can only go ahead. There is no there is still debate that quantum computing is actually very futuristic. They're powerful enough, quantum computers won't come in. But the thing is that it has already created a threat, you know. So there is a chance. We cannot even take 2% chance with a country's defense information. You are getting my point, right? So it's very important to take a measure wherever possible. It is important right now to bring in quantum safe solutions. So definitely it has a future. Okay.
And I think someone asked, when do you think the quantum era will start? When do you think what Q day will be?
For me, I think it happens in as that company's prediction, it should happen in 5 years. We need to completely replace. Maximum could be 5 years, maybe. We need to completely replace, even if it is not Shor's algorithm, as we can say D-Wave. They are producing annealing-based quantum computers. So they are promising factorization problem to be converted into optimization problem. So there is studies parallelly going on like that. So if these computers also get so powerful, still, since as I've told again, already stressing on that point, once there is a threat in place, people start looking at the possibilities of breaking it. So that stage is already here, and we cannot go back now. We have to have quantum safe solutions, and we should be prepared. And it should happen in 5 years.
And then we have a question. Is it only that quantum computers could break? So are quantum computers the only thing that can break RSA, or is there a possibility that classical supercomputers can do that as well?
As we know, Moses, no, it's not Moses, Moore's law. So there is a limit where we can go on the computational rate, right? So we are sort of on the maximum limit where we can go with the classical computational part. So we have sort of attained it. Now, anything beyond that, we have to look at subatomic levels, and that's where quantum lies. So it's like a natural progression that we are making. So yeah, I hope it answered the question. We have to, it's not about having a very powerful classical supercomputer. It's where the computation goes. If we are thinking about this computational transition as going from classical to quantum, it's not like that. It was a natural progression that expected. It is the computational power that got increased. When we went from the normal level to subatomic level, it got increased. So it's like we are having an extended computational power, which is in infancy, but it will get explored and improved in future, and so it will happen. So maybe, as I told, there are other approaches other than Shor's algorithm, like annealing-based factorization solutions, which is based on optimization. So if you know these algorithms difference, one is based on Fourier transforms and all those things, and other is based on optimization. Both are different. So one is period finding problem, and other is optimization problem. So optimization problem can be run on a D-Wave annealing computer. And you guys would have heard what is the prediction of their computer's qubits, right? So yeah, and it is very easy to scale up also. So if D-Wave goes like this, maybe we need not even have a Shor's algorithm implementation. We might be able to factorize RSA using an optimization problem, RSA as an optimization problem. So, but it has complexities if you look into the papers related to it. But yeah, a lot of work are going on in parallel. It's not the Shor's algorithm or the Grover's algorithm alone that is the threat. Okay, threat is in place. People are exploring multiple possibilities right now, And that's the way. I mean, that's the way it is. The environment is right now, and that I should say that is the threat. People are exploring. A lot of studies are going on how we can break RSA right now. Estimations. If you look at papers, resource estimation for breaking RSA, resource estimation for breaking AES, and even me personally, I'm working on cryptanalysis. I got interested in predicting like when these algorithms will break. So yeah, that itself is a threat. So
just to clarify, so there aren't only Grovers and Shores, there are other possibilities, other ways,
yes,
as you explained with quantum annealing, that there are other paths we can take to break RSA.
exactly. We can combine Grover with Simon to make even powerful combination for breaking S boxes and all. So there are a lot of approaches.
And
Not
then,
only like one way. Yes.
mhm. And someone was asking if we can use QKD protocols, why can't we just replace that with the future broken asymmetric protocols like RSA without going into post-quantum crypto systems?
Yeah, that's a very good question, which I also felt like when I was initially learning about the power of quantum cryptography. But once you get into it, you will know the implementational constraint. Like for example, BB84 protocol, as I have mentioned, it requires single photons to be emitted, and you need encoding in that photon, and you expect that photon to reach in that state through the quantum channel to Bob. Okay, so there is a lot of things that is happening, which is like once you get into it, is beyond the complexities that you have in each step is beyond like you can imagine. Once you get into it, that's when you realize there is a lot of things that is going on, and it is not that you can have it in a lab setup. You have to understand that industry should be using it, common people should be using it. If I need to use a QKD protocol on my device should be capable enough to measure these, send these, right? So it's a long step to go. I hope I answered your question, but right.
Mhm. Yeah. And then another question, what math do you need to know for cryptography algorithms?
It's basically linear algebra, then field theory. Yeah, so that's the places where you can start with field theory and linear algebra.
Okay. And another question, so the
Yes.
implementation of
Yes.
post-quantum crypto systems is easier than implementing QKD protocols.
Exactly, you. Because as I've told, post-quantum crypto systems, even though they are like huge in size, like compared to classical crypto systems, they're still looking like classical algorithms, which you can run on my device. Maybe it will heat up a little more, or it will take a little more space. But still, I can run it on my device that we have right now. On each of your device, we can still run post-quantum cryptography. That is a promising thing, right? So that's why we say that post-quantum crypto system standardization is what immediately is possible rather than going for QKD, because vast adaptation of even NIST is predicting post-quantum cryptography adaptation to take 5 to 15 years, I have heard. Like at least I'm thinking it will happen maybe in 5, because you have to understand the current security infrastructure that we have. It did not happen in one day. It took years, right? Like 15, 20, 25 years to be what we are today. So same will happen with this also. We cannot like immediately transition, but post quantum is expected to be standardized maybe in 10 to 15 years. QKD and all will, vast adoption might take even more because of these implementational constraint. Maybe somebody magically solves all the implementation constraints someday, which then maybe that's a different story. But right now, it might take time.
Mm-hmm. So post-quantum crypto systems is just like an easier shift than a complete overhaul that's required with QKD.
Exactly, exactly.
So how do you think that quantum computers can be more accessible for people and companies in the future? And as you said, how can, like, because we want all of these crypto systems and all of these new like quantum security features to be accessible for everyone. We want everyone to be secure.
Yes.
How do you think we can make that possible?
That's where we need immediate standardization of post-quantum cryptography. So if our current public key infrastructure is standardized to adopt PQC schemes, at least for now, because as I told, breaking RSA might take some years. Okay. Now breaking a lattice problem will take another so many years. If somebody like smart enough to bring another algorithm to break lattice problems, that is a different question. But let's take the positive side. Breaking RSA will take, let's say, 7 years. Maybe breaking lattices might take another 10 years. You are good to go for at least 10 years. I won't say 17 years total. You're good to go for at least 10 years. So you get some buffer period for the transition. So yeah, that's where we can immediately have post-quantum resistance. Like simple example could be like having double signatures. So in our TLS, in our web-based applications, we'll have signatures where we maintain the certificates, right? So on the certificates, we are usually using ECC plus RSA combo. So along with that, we'll add one more layer, which also adds PQC signatures. So we are good, at least for some time. So
baby
like,
steps.
yeah, baby steps.
And someone is asking, which is harder, breaking a lattice or a QKD protocol?
Okay, so QKD protocol, I'll say ideally it's unbreakable. Ideally. So BB84 protocol, if it is like implemented in the ideal scenario, like we know that there is observer effect, right? So the quantum channel, any deviations on the quantum channel will be detectable both to Alice and Bob. See, with the classical communication, the problem is that if me and Sabina is communicating, if anyone is copying our information, we'll not get to know. But in the quantum channel, we'll immediately get to know. That's very powerful, right? So if it is implemented in an ideal setup where we restrict the possibilities of quantum, what should I say, sniffing on the quantum channel, copying the photons and measurement and replay attacks, all those possibilities, if you are able to avoid, then QKDs are unbreakable. But they have their own challenges because measurement and replay attacks, if the Eve is very powerful enough, he can do that without Bob Bob knowing that he had done that. So there are measurements and replay attacks and all. Yeah. So as I've answered the question, lattices is again a mathematical problem. So if you will be able to reverse the find the actual solution for the mathematical problem, it is broken. But QKD is based on phenomenons. It's like it's having a different level of security.
Wow, this is really exciting. Like, just such a like a new space, and I'm just so happy that we got to hear you speak about quantum cryptography and like the future and how imminent the danger of like breaking RSA is. I don't think many people understand that. And I think you really underscored that. Like, this is a really big problem because if we break like RSA, like your data is no longer like, it's just in like clear text, basically. Like there's, you know,
yeah,
all of your
That's-
information is basically like publicly available.
exactly. And
Yeah.
it's yes, Elisa.
Yeah, I'm sorry. Thank you so much for sharing. I think that you clearly have this motivation, and yeah, I'm so happy to have you here. We are so happy with Sabina. So yeah, I personally could learn a lot, And yeah, so happy. So after this, we're going to share all these talks in YouTube for everyone to like keep reviewing the concepts and everything. So really, really happy. I appreciate it.
Thank you. I'm so happy that the message is conveyed, and yeah, you guys could be bringing out promising solutions in this area. So that's what could be more exciting.
Yes, thank you so much. So now
Thank you.
we're going
Thank you.
to,
Thank you all.
thank you. So now it is